All right, guys, we're going to talk about horizontal projectile motion today. Most important to remember, like this slide says, is the horizontal component of motion for a projectile is completely independent of the vertical component of motion. So even though this girl, she's throwing the ball here, and she's throwing it at an angle. So what we've got to get used to doing, guys, is she's throwing it at this angle here, but we've got to get used to looking at the components of motion. There's a vertical component of motion right here, and there's a horizontal component of motion. And we can treat them independently of one another, which means they don't depend on one another. Okay, a projectile moves in two dimensions. It therefore has two components, horizontal and vertical. Now, if we look at this projectile here, we can see two vectors at every point. There's a vector for the vertical component of motion, and there's a vector for its horizontal component. And what do you notice about the vertical vector here? What's it doing? Is it changing or is it staying the same? It's changing. It's going really fast at first. Now, why does it get smaller as it goes to its apex? Because gravity is slowing it down as it goes up, right? And then what happens as it goes back down? Well, these vectors get larger because gravity is accelerating it toward Earth, so they get larger. Now, let me ask you this. What do you notice about these horizontal vectors, the blue ones? They're constant, yeah. Gravity does not act horizontally. It acts vertically. So remember, we're going to ignore air resistance. So we're going to assume that the horizontal component of velocity is constant. Okay, so the horizontal velocity is constant. Just like we said, that's why the blue vector is always the same length here. Horizontal velocity is constant. I think you're supposed to write that down. Hopefully you have your guided notes out and are writing this. But why is horizontal velocity constant? We kind of just talked about it. Why? Yeah, gravity doesn't act horizontally, and we're ignoring air resistance, so it's always going to be constant horizontally. But let's talk about vertical now. Acceleration due to gravity, which is given this symbol lowercase g, acts only in the vertical component, and its magnitude is negative 9.8 meters per second squared. Again, why is it negative, Dawson? Because it's going down. Good. And down in physics is negative. Now, if we combine these components together, the horizontal and vertical components produce the path for the projectile. So if we averaged out these vertical vector and this horizontal vector, we would get a path that looks like this. Okay? That path is given a name. It's one of our vocab terms for this chapter. It's called trajectory. You're supposed to write down the definition. So an object's trajectory is the path the projectile takes in the air. It's that path that it takes in the air. We say it's the object's trajectory. This path that it takes in the air, this trajectory, is called parabolic. And we talked about that in the previous video, so I think we'll just move on. Okay, horizontally launched projectiles. We're going to talk about this today. We're going to launch them directly horizontally. We will first look at the projectile's horizontal velocity. And so we're going to look at the velocity going directly horizontal. They have no upward trajectory. So they have no initial vertical velocity. So that's why you see right here, velocity initially in the y direction is always going to equal 0. Whenever something is launched horizontally, it's like you just drop it. Initially, its vertical velocity starts at 0. And so that's going to be an important thing to remember. If it rolls off the table, it's just like it was dropped off the table. Its vertical velocity has got to start at 0. Now, what happens over time to its velocity? it increases, and that's because gravity is accelerating it down. But it starts at 0. Okay. Okay, let's do a few practice problems, and I think it will make sense. Practice problem number 6. Please write down everything that I write down with this problem, okay? So let's read it, and then we'll draw a picture. It says, you roll a ball off of a 0.85 meter high table. The ball leaves the table with a velocity of 2.5 meters per second. How far will the ball land from the leg of the table? So here's my picture, and you guys should draw a table, and this ball is rolling off the table. Okay, it's got a horizontal velocity of 2.5 meters per second. And we know its trajectory. What is its trajectory going to look like? Well, let's draw a dotted line. It's kind of just going to be this rainbow-like shape till it hits the ground, this parabola-like shape. And we really want to know how far the ball will land from the leg of the table. So if we measure from the leg of the table here, out on the ground, we want to know how far that is. Okay. What do we call that, how far it is horizontally? What is that known as? What variable? Isn't that displacement?
Oh, yeah.
Horizontal displacement, we don't know what it is
So
yet.
wouldn't that be exactly the same as if you just rolled the table or rolled the ball on the ground? It would be like the same amount of distance.
Well, on the ground,
So instead of like pushing it off the table.
yeah, exactly right. Exactly right. Okay. Yeah, and that's because horizontal velocity is constant. But then if you rolled it on the ground, wouldn't there be friction that would slow it down? So we could consider that as well. All right, so before I give you the answer, let's solve it. Okay, first step in solving these problems is draw a picture, which we did. Hopefully you've done that on your notes. Step 2, we're going to list vertical and horizontal. Okay, we're going to separate this object's motion into these components, its vertical component and its horizontal component. Now let's list the variables. Remember that there's always the 7 variables that we need to account for. Let's just start with initially. What's time initial, guys? 0. Time always starts at 0. What's velocity initial? Vertically. 0. It's just like you were to drop it, right? So it starts at 0. Now, of course, it's going to speed up as it goes closer to the ground because of gravity, but it starts at 0. What is displacement initially? We're going to call that point 0. Okay. Here's one that you should know. What's acceleration? Negative 9.8. And that would be meters per second squared. What is velocity final? Do we know how fast it's going right before it hits the ground? Did it tell us? No. What is time final? Do we know how long it's in the air? No. Nope. So put a question mark on that one as well. And this one we do know. What's displacement final? Good. If we call this point at which it falls off the table 0, the initial displacement 0, how far down was that table? Did it tell us? 0.85 meters high. So from here to here is 0.85 meters. That means our displacement is going to be what? Negative 0.85 meters. How come it's negative again? Because it ended up below where it started, and so its displacement will be a negative number. Okay. Now let's list our variables that we have to list horizontally. And if we look at our equations, this is the only one that's the horizontal. So this is our only horizontal equation. So we just need to know displacement horizontally. Do we know it? Do we know this displacement horizontally? No. Okay. Do I know velocity horizontal? Yeah. It told us that it left the table at 2.5 meters per second. And do we know time, that it's in the air horizontally? We don't. So I'm going to put a question mark there. Okay, so there are all of the variables that you need to list for these problems. Okay, so take some time, draw a picture, list your variables. Now, we really want to know how far from the leg of the table the ball will land on the ground over here. That is horizontal displacement. So what I like to do is put a box around it, circle it. That's what we really want to solve for. However, if you look at equation number 1 here, can I use it yet? And the answer is no, because I don't have displacement, so I don't have this variable, and I don't have time. So there's no way I can use it. So this is going to be a common theme in these problems. You're going to have to solve for time with a vertical equation first. Now, the time that it's in the air vertically, isn't that the same as the time that it's in the air horizontally? And the answer is yes. So once you have found the time vertically, we're going to plug that in for time horizontally, and then we can solve for the displacement using equation number 1. Okay, that's the step we're going to take. But now that we're going to solve for time vertically, we can only use 2, 3, 4, or 5. Which one should we look to first? Which one do we use the most often? 4. So let's just go ahead and look at 4 and see if we can use it. Do I have displacement vertically? Yeah, we do. It's negative 0.85. Do I have its initial velocity?
0.
Yeah, it's 0. Do I have acceleration?
Yes.
Yeah. So can I use this equation? Yeah. And the answer is yes. So let's write it down. Let's write that equation down, and then let's plug in our variables. What's displacement vertically, guys? Is equal to, what is its velocity initially? 0. So that whole term goes to 0. Plus 1/2 times a negative 9.8 times t squared. Okay, now let's simplify this a little bit. We've got a negative 0.85 is equal to half of a negative 9.8. Isn't that a negative 4.9 t squared? Okay, now how do we solve for t squared? Yeah, I'm going to divide by negative 4.9, both sides. Cancels out over on this right side. And so negative 0.85 divided by a negative 4.9. Yeah, okay, so 0.17 is equal to t squared. Now let's remember, how do we get rid of that square on the t? Square root. So if we square root this side, do I have to square root the other side as well? And you do. So let's take the square root of 0.17, and that will give us time. The time that that ball, or whatever it was, it was a ball, was in the air, it was 0.41 seconds. Okay, is that what it wanted us to solve for? No. But if we have time vertically, 0.41 seconds, can we plug that in horizontal equation? Okay, let's do that. Our horizontal equation is this one right here. So displacement is equal to vt. We don't know its displacement. The velocity we do know was what? 2.5? 2.5. And let's times it by the time that it's in the air was 0.1 or 0.41. 1.03. Is that what you guys got? 1.03. What are the units for displacement? Meters. Okay. Okay, so if you measured out 1.3 meters away from the leg of the table, that's where that ball is going to hit. Okay? And that's kind of cool. We can figure that out. That's kind of what your test is going to be like for this chapter. You're going to have to place a cup over here, and the ball that's rolling off, well, you'll have to predict how far away from the table you've got to put the cup so that the ball hits it. We can do that now, right?
Yeah.
Okay. All right, let's continue on. I've got a number of practice problems. Let's see if we got that right. 1.04, 1.03, yeah. Hey, that's a good point. How come I'm off by a 1/100th of a...
Because we're rounding.
Because we're rounding. Guys, if you don't round, you'll be more precise, right? If you take the decimal out to more than just 1 or 2 decimal places, you will be more precise. Correct?
Yeah.
Okay, so be careful with rounding. All right, practice problem number 7. What I'd like you to do is to try this problem on your own. I want you to draw a picture. I want you to split the vertical and the horizontal components of motion up. List all the variables. And try to solve this one on your own. I'm going to hit pause, so I would like you to hit pause on your video and try it on your own first. Okay, so I went ahead and drew the picture, and I listed the vertical and the horizontal components of motion and all of their variables here. So hopefully you were able to do that on your own. Now let's go ahead and solve it. Again, this problem is exactly like the last one. We want to know how far away from the leg of the table the ball will land. So we're looking for horizontal displacement. So what I would do if I were you is put a box around it or circle that variable. That's the one we really want to know. And just like the last problem, we don't know the time that it's in the air, so we can't use equation number 1 yet, because we don't know displacement and we don't know time. So what we're going to be looking at with these problems, always look to equation number 4 first. That's usually the one we can use. We're going to use it to solve for time. And then once we have time vertical, we can move it over here. That's the same time as it is horizontal, and then we can solve it. So I'm going to take it to that point. So that's what I would like you guys to try and see if you can solve for time vertically using equation number 4 and see if you can do that. Okay, so I went ahead and solved for time using equation number 4, and hopefully you were able to make sense of what we did here in equation number 4. And time came out to be 0.49 seconds. So now what we'll do is take that time and plug it into a horizontal equation, equation number 1, and see what the displacement is. Okay? So again, we're going to use this equation. Displacement is equal to velocity times time. We don't know what displacement is. What was velocity horizontally? Remember, we're looking horizontal now, so it's 4.25. And now that we know t was 0.49 seconds. You can plug that in. So the displacement for this question is going to be 2.1 meters. So if you measured out 2.1 meters away from the table and placed your mark, that's where the ball is going to hit. Okay. Did anyone else get that? Verify that? Okay. 2.08. Very good. That's close. Yep. Okay. Yeah, if it's just a rounding issue, you won't miss it. But again, like I said, if you will take it out to many decimal places, you'll be more precise. All right, let's try another one. A little bit different here. Practice problem number 8. It says you're standing on a mountain that is 2,000 meters high. You shoot your rifle horizontally, and the bullet leaves the gun with a velocity of 960 meters per second. How far will the bullet travel before it hits the ground below? I'm going to hit pause on the video. What I would like you to do is draw the picture, list the horizontal and vertical components of motion, and all the variables. And then we'll pick it up from there. So please hit pause on your video and try taking the problem to that point. Okay, so hopefully you were able to take the problem to this point. You've drawn a picture. You've listed the horizontal and vertical components of motion and all of their variables. Okay, remember the vertical has got 7 variables. Horizontal has 3 different variables you need to list. Hopefully your variable magnitudes look like that, because that's what it is. What this problem is really asking us for is how far does this bullet land from the edge of the cliff? So we're looking for this displacement right here, which is a horizontal displacement. So if I were you, I kind of like to box or circle what we're looking for. Horizontal displacement. So of course we're going to have to use the one horizontal equation to solve for it. But if I don't know its displacement and I don't know its time, can I use that equation yet? The answer is no. So what I would do is solve for time vertically. Okay, so let's figure out what the time that's in the air vertically is with a vertical equation. Usually equation number 4 will work. Okay, so I would look to that one first. If it doesn't work, try another one. But in this case it will. So that's where I would like you to take the problem from here. Write equation number 4, plug in all the variables, and solve for time using this equation. And then hit play and see if you got it. Okay. Once you have time vertically, we can plug it into our equation number 1 and solve for the displacement horizontal. So let's take it to there. I'm going to hit pause. I'd like you to hit pause on your video and try it on your own. Okay, so I went ahead and I used equation number 4 right here, and I plugged in everything. And if you did your math correctly, you should get the time that's in the air is equal to 20.2 seconds. Now that we have the time vertically, we can take that 20.2 seconds and it's going to be the same time horizontally. So now let's use equation number 1, which is our horizontal equation. Now that we have time, we can solve it. So displacement horizontal is equal to its velocity horizontally. Now, what was its horizontal velocity? 960, yeah. Times the time that it's in the air was 20.2 seconds. And I get the displacement is equal to, let's see, what is that, 19,000? 19,394.85. And is this going to be in meters, guys? Meters.
Yeah.
Okay. That's a long ways. Now, of course, in reality, is it really going to go that far horizontally? No, because what? Air resistance. But, I mean, air resistance is kind of small when you're considering it, but over 20 seconds, it's going to be kind of large. So, if I was to say how far that bullet's going to go, I would estimate lower or less than 19,394.85 meters. That's a lot of miles. You could ask Siri, how many miles is 19,394.85 meters? And figure out how many miles that is, but that's a lot. Okay? So, anyway, it's not safe to do that if you're ever on top of a mountain. Okay, let's see if we got it right. 19,395. Yeah, if we round that 0.85 up, we're right on. So, good job. I've got one more practice problem for you to try with this type of problem. Practice problem number 9. Let's read it. A plane traveling with a horizontal velocity of 100 meters per second is 500 meters above the ground. At some point, the pilot decides to drop some supplies to a designated target below. A, how long is the drop in the air? And B, how far away from the point where it was launched will it land? Okay, so a very similar problem to the ones we've just solved. I would like you to draw a picture, separate its vertical and horizontal components, list all the variables, and solve this problem. Okay, I'm gonna hit pause. If I were you on watching this video, hit pause on your video and try this one. Try to go all the way to the end and get an answer, and see if you can do it correctly. Okay, so I went ahead and I finished up the problem. Hopefully you were able to draw a picture here of what was going on. Break your vertical and horizontal components of motion up. List all 7 variables for the vertical component and 3 for the horizontal. And hopefully you got the magnitudes that I've got listed here. Okay, then it was very similar. We wanted to solve for displacement horizontally, but we didn't have time, so we needed to solve for time vertically. So what I did was choose equation number 4, solve for time, and I got 10.1 seconds. So that supply drop is that is going to be in the air for 10.1 seconds. And once we know how long it's going to be in the air vertically, we can slide that up here. For time, it's going to be the same horizontally. So this was also 10.1 seconds. And then you can pick equation number 1, and that's what I did here, and solve for the displacement horizontally. So if this is 1,010 meters, whoever is dropping the supplies needs to release it 1,010 meters before the target zone, or whoever's picking up the supplies down there. And then it will land where you want it to land. So hopefully you were able to solve for both time and for horizontal displacement there. Guys, that's it for horizontal projectile motion. To give you some more practice with it, I've got horizontal projectile worksheet in the student workbook. So again, it's horizontal projectile worksheet. Please go there in your student workbook and complete that. And hopefully this video helped.